Hello everyone, welcome to the Data AI Summit session on determine when to use GPU for your ETL pipeline at scale. And this is very important because we have many different jobs, and so it's very hard to determine which one manually. So the purpose of today is that to us to determine what jobs can use GPU before you even go down the conversion path, right? And I'm Chris Vo from AT&T, and with me I have my co-presenter, Hal from NVIDIA. Okay, so today agenda, Hal will go over the under the hood of the qualification tool for Rapid GPU, and then I will go over how AT&T use the tool at scale, and then we will do some cost saving, and then the key takeaway, and then what's next for AT&T. And then now, Hal, go ahead.
Sure. Thanks, Chris. Hi, everybody. Good afternoon. My name is Hao, and I'm from NVIDIA Spark Rapids engineering team. So I manage a team mainly for customer engagement and Spark application engineering work. So this is our second time of sharing a story on Data AI Summit. So let me give you a recap. So last year, Chris and I had a session on how AT&T migrated one ETL job to Spark Rapids on Databricks with pretty good speed up and cost savings. But how many of you have ever heard of Spark Rapids? Can you just raise your hand? Whoa, lots of those. Great, that's a good news for us. So I still want to quickly introduce Spark Rapids here, right? So the full name of the Spark Rapids is Rapids Accelerator for Apache Spark. So in simplest words, so it can make your Spark jobs run GPU much faster and much cheaper. So however, not every type of job is good candidate for GPU. Can you have a guess what type of Spark job are good candidates for GPU without any price or freebies? Can you just have a guess? So the answer has 3 keywords. Can you just get one of them? Duration. What else? Sorry? Okay. So yeah, let me just show you the 3 keywords. So basically the 3 keywords are computation, computation, and computation. So it's a single word, right? So Spark Rapids really loves the computation-heavy jobs, such as large hash aggregate, the joins, like sort merge join, shuffled hash join, and nested loop join, and sort, right? Those types are really good candidates for GPU and for Spark Rapids. So let's imagine companies like AT&T, right? So a single team, they may have like hundreds or thousands of jobs running on Databricks.
Okay.
How could we easily identify which job is a good candidate for Spark Rapids, right? So after our engineering team brainstormed for a long time, so we come out with 2 possible solutions. So the solution A, so let Hao and Hao's team work 24/7 for a whole month, working with AT&T to manually look into every query plan in every job. So that's option A. And option B is create a tool to do this work. So they ask me, which one do I like? I vote for option B without any hesitation. That comes to my first slide here. So here we come out the qualification tool, right? So the qualification tool works by evaluating the Spark event logs. So an event log contains granular details about what's happening in a Spark application. So it includes the details about the SQL plan, including the order of operations, and details on data sources that were used throughout this job. Additionally, it contains information about Spark execs and expressions were run during this job. So these execs and expressions are essential for this tool to understand what part of this job could be accelerated by GPU using Spark Rapids. So the qualification tool, right, it examines the various operations in the Spark application by looking at the tree hierarchy here. So the tree for a given stage in the application will include a hierarchy of SQL nodes, execs, and expressions. the tool traverses the node trees to analyze what nodes, execs or expressions, would be able to run GPU, and what read and write formats were used during the I/O operation for this job. For example, it could be Parquet, it could be ORC, it could be Hive text file, right? So there are different read and write formats there. And for nodes that are applicable to run the GPU, the tool will give you a speed up factor to estimate how long the same node would take if executes on GPU cluster using Spark Rapids. So the speed up factor are determined by running the NDS benchmark of 100 queries and comparing the GPU to CPU and measuring the speed up for each exec. We run the benchmarks for different CSPs like Dataproc, Databricks, AWS EMR, right? And when we run the script for that CSP, we are using the speed up factors that are measured for the environments and the Spark distribution. The qualification tool speed up factors are updated in each release of the Spark Rapids plugin. So every release, we have a new speed up factors information there. And it's also open sourced in our GitHub repo. So the tool will take the Spark event log as input that are generated from Spark 2 or Spark 3 on the CPU Spark cluster. And the qualification tool supports both of the versions from different Spark. And the event log are then processed by the qualification tool to generate application level recommendations, estimate the speed up and cost savings, along with detailed metrics at the exact and stage level. So here is output of the qualification tool. It comes in the format of the text files, shows results of analysis, right? So the basic output shows the application name, whether this application is recommended or not, right? Normally there are three options there. It's a strongly recommended, recommended, or not recommended. And a speed up factor if you run the same cluster shape, but with GPU nodes added. The estimated GPU duration versus the duration in the CPU event log, and the estimated savings based on that CSP's retail pricing. This is a summary table provides overall estimate speed up and estimate cost savings. The quantification tool provides an estimated indication of speed up only. These speed up are not guaranteed. The purpose of this estimate is to provide users with queries they can start to focus on when using this plugin and the potential savings there. So users may want to consider the total cost of ownership, which is called the TCO, of these jobs by considering the job frequency to see which jobs might give you the most cost benefit if they were sped up by the GPU. We are working to enhance our tool to infer frequency based on a given set of logs and make recommendation accordingly. In addition to this output, more detailed information are in some other files, including information about why an application may or may not be well suited for GPU. And the output contains information about the execs and expressions supported on the GPU, their duration, speed up factors, and the estimated speed up by stage for each application. So there are more detailed information, not just this one. So the text format is just like one way of presenting the results of the qualification tool. The qualification tool also outputs HTML files for easy navigation of the output results. The UI shows the same information as the text with a summary of the time spent in the SQL data frame operations that could be supported on the GPU, which is showing here as a GPU opportunity, which is 1.1 hour here. So with this UI, users can navigate into each of the application here and get more specific details about the results. Of course, you can just do the search here to see which application is recommended, which application is not. So the Spark Rapids user tool is available as a pip package and is downloadable from the Python package index. It can be installed and run locally on a laptop or workstation as long as you have the access to the Spark cluster. So you just need to pip install on your, let's say, Mac, if you're using Mac. I think that's all for now, and I will hand it over to Chris for the rest of the slides.
All right, thank you, Hal. Okay, so basically, what Hal mentioned is that the qualification tool, you run it on a specific, you passing in the log file for a specific cluster execution, and you get a recommendation whether that execution, it could be a job or a query or something, should be using GBU or not. But that's only for one instant, right? For one job. What happens is that we have like hundreds of jobs. So what we do is that there's no way that we manually run each one, and also we don't want to run during the day and all that. So what we decided at AT&T is that we take the tool, this new toy, and we do is that we from the left side of the slide. Basically, what happens is that we have all the job lists that we ran from Workspace, right? And then for each of those jobs, we pick the latest execution. So from the latest execution, we know what is the cluster that it run on. And then from that information, we will create another job. So basically, we have a lot, and then from each of those, we create a job, and include multiple. And for each of those, we pick about, each time we run, we pick up about 5 of the sample and run. Because the reason for that is that at the early stage, the tool is written in Java, so there could be some memory issue or something. So as it's run, it doesn't clean up properly. So what happens is that when you start doing that as a batch of 5, then sometimes the cluster will kill itself after it's run, and also it's cleaned up, and also less memory issue. But anyway, so we pick a sample of 5 of those for each of the time it run. And what it does is every time it runs, it will call the qualification tool. And the qualification tool execute and then output the result into a log file. And then we parse that log file, and we got the one single number that's very important to us, which is what is the hour saving, right? So like how was mentioned, it's like 1.1. That means we assume that mean that if you're using GBU, then you will save about 1 hour worth of execution. But basically, that's what I mean. Not clock time hour, but execution hour, okay? So with that number, what we can do is that we start to aggregate all this number, because we have the execution of individual job on the CBU already, and we don't know the size of CBU, so we know how much it costs individually for that job. So let's say that if the execution per hour costs about $1, and we save, and this mean that we can save one hour, and it's only $1. So it's just literally math at this point. So once everything is done, we have everything aggregated. So again, from the left-hand side, we have the name of the job and who is the owner, so that we can contact them for the conversion. And also the tool output will be recommended or strongly recommended, so we only pick all the recommended or strongly. Everything else we throw away. And then the main thing is, like I said, the saving hour. That's just the estimate hour that we got directly from the tool. And then we know exactly how is the cluster size, so we know how much it costs. So we multiply that number, and then we come out to be what is the saving every time that job is run. Okay, here's a keyword. Every time the job is run. That means that sometimes the execution, the qualification tool can say that for this specific job, you save a lot of money, but if that job only runs once a week or once a month, it doesn't matter. But let's say, there's some job that's saving just a little bit, but the frequency at which it's run, let's say it's an hourly job, that makes a big difference. So that's why we aggregated, we check to say, okay, if this job runs for the whole year, how much it will save us. And that's why you see the number on the right-hand side. And we order them in reverse order, because there's so many jobs, we have to figure out which one is the good candidate so that we can start converting them first. Because if we convert every one of them, it's not economical, right? So basically we have a checklist. So at AT&T, we decided that any job that is have a potential saving of $10,000 a year or more, then we will go for that. Everything that less, we probably save it for another day, right? So that's for that list. And then for each one, when we convert, the conversion is very simple. All you have to do is just no code change. You just have to change the configuration of the cluster. First of all, to use GBU, and also some configuration change. And then once you execute it, it will either fail or not, right? And then I will go over detail of what to do. And for us, we will just record the execution time and the cost of the CBU before and the cost after, and we just subtract the two, and whatever the highest saving, we get it. If the cost is about the same, then we go back to CBU. The reason for that is that GBU is expensive. Not expensive, sorry, GBU is very scarce. so we want to use it for other workload, right? So we don't want to use, because there's a limited GPU, as you can find out from each of the workspace, okay? And of course, when you convert over, and then if something fail, if it's something simple, then we will fix the configuration. But if it's something major that we don't know about, then we just go ahead and convert back to CBU and just leave it on there, okay? Okay, so this is a typical CBU configuration at AT&T. So we have like a policy to make sure that everybody follow the same good practice of all the, like for example, shut down a certain time and all that automation. And then the key thing about this is that we want to benchmark with CBU to GPU. We don't want to deal with the Photon at this point because there are some jobs that Photon, and we ignore them for now. Okay, and then that is all. Okay, so basically for the GPU equivalent, if you look at it, it's almost the same. The only difference is that it's ML, so using GPU, and then we're using the T4 for execution. And then the keyword for the configuration to use rapid GPU is the SQL enable, the rapid enable. And then there's some other parameter around it to help with the memory management and so forth. But the key is that pink one that I highlight. And then the other one is that you have to have a jar file that is rapid, right? And then the way to install it is that you just install it into the Databricks library. Okay, and so when it's run, and then if you really want to be sure, you will see the differential easily. But if sometimes you don't see the differential, or you see that it's run slower or something, then what you can do is you can check the query plan of each of your jobs. You can pick a few. You don't have to pick everyone. Just pick a few query, and you will see that with the regular CBU node, you should only see like normal, the thing. But with the GPU, then you will see everything is prefixed with what's GPU on your query plan. If you don't have the GPU on every single line, that means that it falls back to CBU. So the way it works is that it will try to execute all your command in GPU. And then, but if a specific operation, Spark operation that it cannot be handled by GPU, because Rapid haven't implement that, then what it does is it roll back to the Spark CBU to execute that, and then it bring it back to GPU. So basically, it have an adverse effect. So what happened, if you see that case, then you just have to reach out to NVIDIA team and say, we need to implement this operation in GPU, and that's it. And they have a quick turnaround. Okay, so basically at the end of the day, once you convert, everything is good, then how do we figure out what is the compute cost, like Hal mentioned, okay? So the compute costs are two factors. First is the VM cost and the DBU cost, right? So because the reason it's important is that you can just look at the DBU. The reason is that with the NVIDIA GPU, the VM is a little bit more expensive than the CBU cousin, right? So basically, we have to take those into consideration before, and then to do the calculation. And of course, last year we already talked about this, so I don't want to go over. You just go look up the price and the DBU, and then you can, depend on your cluster, you multiply by the DBU price for that. So usually a job cluster costs you 35 cents per DBU. The interactive cluster will cost you about 55 cents per DBU, and each company have a different rate because of the vendor thing, right? Okay, so, and then what we do is that we convert every one of them that we pick, and then we convert, and then we have a final list. So what happened here is that this is the result that we got. So we job contact, and then the frequency at which the job run, and then we have the CBU cost, which is the before, and then the GPU cost after. And then from that, we subtract the two, and then we see what is the savings. So for example, the first line, we have about $4.68 every time we execute. But because that one is a hourly job, so we have to multiply by the 8,760 time factor multiplier, then that becomes a 41,000 savings. So basically, by the time that we convert that, and if that one run for the whole year, we will have $41,000 saving for that specific job. So, and then again, we go down the list. And this is actual data. I just changed the name so that we don't have, but anyway. So we have about $1 million saving for this exercise. And then this is just one workspace. We have multiple workspace at AT&T. So, okay, so the key takeaway for this is that the qualification tool will identify the candidate that, that is good to convert to GPU, but it's not always the case, but it's a good start, right? And then also, but when you actually do the convert, but based on that number, you can kind of estimate to see how much you will potentially saving, and it's whether it works for you to go down that path or not. And then once you convert that, But also to choose a candidate, you want to choose it based on the frequency too, because you're gonna just say, okay, this one is give you $5 saving per execution, so therefore it's better than the one that's $2. Because when you take the whole picture in, then it will change your thing. Okay, and what's next for AT&T? So as you can imagine, we have a pipeline that we can find all the job, we aggregate the data, we know exactly which one to convert, but then after that, it's a human conversion. We don't want to do that. So the next step for AT&T is that, and also we have, we run the CBU, GBU, and Photon, right? So the idea is that we have an automation process that can go in there and say, okay, with CBU, let's say that if somebody starts out with a CBU with a 5-node cluster, sometimes that 5-node cluster is not efficient for that because you may only use 2 nodes, right? So basically, we have automation that go there and say, okay, so you start out with 5, but then if whatever, let's say it run for 5, let's say it run for 10 minutes with 5 nodes, maybe you can go for 15 minutes, which is a little bit longer, right? But only using 2 nodes. So basically, we reduce the number of nodes for ECU. And then once we have an optimal number for CBU, then the next step is that we're going to try with GBU and same thing, and then we can go back down. And then we can try with Photon. So basically, that automation will kick in and do that automatically based on the job run. And then at the end of the day, so we track all those numbers and so forth. So that is our next goal for that, automate the whole thing. Okay, and then hand back to Hal.
Yeah, I think this is enough slides. So what's next for NVIDIA is NVIDIA offers the rapid accelerator for Apache Spark for customers like AT&T, right, who want an enterprise-supported version of this software. So it's available as part of the NVIDIA AI Enterprise Software Suite, which is called NVAIE, and is currently supported on different CSPs like Amazon EMR, Google Cloud Dataproc, Databricks running Azure or AWS. So as you have learned, right, so using Rapid Accelerator for Apache Spark offers many advantages. For example, the faster execution time, and also reduced infrastructure cost. And when you purchase a license for Rapid Accelerator, right, so you receive the backing of the full enterprise support. NVIDIA will work with you on fixing bugs, I hope not, and solving problems, and helping you get the most out of your investment. So if you want to learn more, please visit this URL, which is nvidia.com/spark. I think that's everything for today. Any questions or?
Thank you.